Thank you also people from CSCS for inviting me and organizing the workshop. So yes, I'm going to try to explain a little bit what CP2K is and what it's doing with a focus on the parallel algorithms. And I'm first going to talk about the more traditional capabilities of the code, which is DFT, DGEMM, as some people might know in the audience. And then at the end of the talk, I will talk more about the new developments, and also that was John suggesting, that allow us to really scale to thousands of cores. So I like this picture. The code is mostly developed in Switzerland. It's a kind of Swiss Army knife of molecular simulation. It can do a lot of things, from DFT simulations to classical simulations, using all kinds of different methods. So it's tried of kind of listed here. So various ways to describe molecules and systems. So it can be used in fields like chemistry, but also biology or material science. We try to focus on dynamics that is necessary to look at complex systems. We want to go beyond just simple gas phase molecules. We would like to look at interfaces and things like that. So that is the more appropriate picture of the code. It is a more complex Swiss Army knife. Now, CP2K is best known for its ability to do ab initio molecular dynamics simulations that is based on density functional theory. And the focus is on the description of relatively large systems. And that is kind of systems nowadays we can treat quite easily that contain about 2,000 atoms. So these are just fancy pictures, more from the biology field. A DNA crystal or even a small fully solvated protein can now be computed using DFT techniques in a couple of hours, even on machines much smaller than raw. So that was calculations done on the XT3 we had before. Now, maybe more important for science are not really large systems, but the capability to do ab initio molecular dynamics simulations, that is, to try and study the time evolution of your system by computing energies and forces and propagating your system in time. And with that, we can do something that is called a simple liquid. Liquid water is presumably the most nasty and most difficult liquid to simulate, which is, of course, very important. But we can increase in size. We can add solutes to the liquids. We can look at chemistry in solution. Or what is going to become much more important in the future is trying to look at complex systems, interfaces, for example, between solids and liquids, and reactivity on the surface of these interfaces. That is very important. Lots of the material science is like tuning interfaces, trying to get interfaces to do the right thing. Now, before I delve in the parallel algorithms, I would like to point out that some of the good science we do also requires a kind of embarrassingly parallel simulations. So we don't need to do only very large scale calculations. We also need to, for example, gather good statistics by repeating runs. Or, for example, and I will go a little bit in more detail, the key quantity we would like to get out of many simulations are free energies. Because free energies, they are crucial quantities. For example, they are required if you want to understand the binding affinity of a drug to a protein. You have to be able to compute the free energy difference between the drug in solution or the drug bound to a protein. Or if you're some people that are in combustion, yesterday asked me, if you would like to compute the rate of a chemical reaction, which is of course crucial, you have to be able to compute the height of the barrier between reactant and product. And in small gaseous systems, that's easy. That's just total energies. But in complex systems, we have to do free energy calculations. Now, free energy calculations, they are well established. You can obtain them as the integral from the reactant to the product of a certain quantity here, dH d lambda, which you can evaluate for every value of lambda by doing a long ab initio molecular dynamics simulation. On the order of 10 picoseconds, that's for us a long time. That typically means for each value of lambda, about 20,000 to 100,000 CPU hours. So it's obvious that if you want to evaluate this integral, you can parallelize also over lambda and parallelize over the evaluation of the integrand. So that is just an example of a very important kind of embarrassingly parallel approach also needed in ab initio molecular dynamics simulations. Now, I want to focus on basic computational DFT. So the thing that these codes are trying to compute, what we have is a total energy, this E here, that is a function of a matrix of unknowns, the P. The P is called the density matrix. E is the total energy. This is the basic functional of density functional theory. It has the kinetic energy of the electrons. It has the interaction of the electrons with the nuclei. And it has a very difficult or computationally demanding term that is the Coulomb repulsion between the electrons. And if you take the definition of n, and n is the electronic density, you can see that it's a double sum, and the indices mu and nu increase linearly with system size. So formally, this term is going to scale with the system size to the 4th power. So if you want to increase double the system size, this term would become 16 times more expensive. So that is a real problem. We would like to eliminate this term. And the main breakthrough that made CP2K an efficient code is a new algorithm to compute this term. And I will go in detail how we do that. Now, there are two things. We cannot just, we could compute this energy for any given matrix P, but we want to have the optimal P. We want to find that P that minimizes this functional. So there are two steps. We want to compute the energy and the derivatives of the energy with respect to P, and we want to optimize this functional with respect to P. It's a fairly complicated optimization because there are constraints on P. It's not an unconstrained optimization. It is a constrained optimization problem. Now, let me focus on, or let me first tell you the main idea. So this is an expansion of your density in basis functions, and there are traditionally two kinds of basis functions. The solid state community has been using plane waves a lot. That is cosines and sines. They are ideally suited for condensed phase for metals and things like that. And then the quantum chemical community that has been looking much more at molecules has been using localized basis functions, atom-centered basis functions like Gaussians or linear combinations of Gaussians. Now, both methods have their advantage, and we try to combine in CP2K the advantages of these two different worlds. So we use as basis functions Gaussians. They have the advantage that they are localized and very compact. So with a relatively small basis, we can get a good description of the wave function. But we also use the plane waves to compute the electrostatics. And that I want to show here. That's the main algorithm of CP2K, how we get a linear scaling calculation of the Coulomb interaction between the electrons. The idea is that this term, this is the density represented in the localized basis set, can be transferred in a different representation. We can transfer this density on a regular grid. Then we can FFT this regular grid. And in Fourier space, the Coulomb problem is trivial. You can solve it directly. And then you can compute the Coulomb repulsion and all quantities you need, for example, the matrix elements corresponding to the Hartree energy. And all these steps can be made linear scaling. So we go from a formally m to the 4th algorithm to a step that is basically just linear in m. You could argue the FFT is not linear scaling, it's m log n, but for our measure that is still linear scaling. So the idea here is that these basis functions are localized. So if, for example, two atoms are far apart, the overlap of these localized basis functions is 0. So we only have to consider a constant number of nearby basis functions, and that's just a linear number of non-zero products in this sum. We can map them on a local range. I mean, the Gaussians decay very quickly, so with a constant effort, we can map them on the grid. And then when we have this density on the grid, FFTing is also a traditional approach. Now, that's the basic idea. Now, the question is, do we get what we promise? I mean, this is actually measured timings. So this is the cost of basically computing the Coulomb interaction energy for increasing system size. And indeed, you see quite nicely that scales linearly with system size. And that's the big thing. So we have an algorithm that scales linearly with system size. This is just for comparison. The fraction of time spent in the FFT, in this case, is shown here. You see it's not really dominating the total calculation. And also, for us, this is close enough to linear scaling. The other nice thing is it scales linearly also for very small systems. So this linear scaling starts not only for huge systems, but also already for small systems. We are in the favorable regime. Now, that was an explanation how we deal formally with this term. The other part is how we minimize this energy with respect to the density matrix. The traditional way is to compute the derivative of the energy with respect to the density matrix. That gives you another matrix. And diagonalize that matrix and do that in a self-consistent way. So repeat this diagonalization over and over. Now, we have a slightly better way that basically transforms the molecular orbitals, that is the expansion of your wave function in the basis set, in this kind of seemingly complex-looking functional of x. So this C is a matrix. X here is also a matrix. And these are the new variables we use in a direct minimization. And the nice thing about this transformation is, well, there are two nice things about this. It is only linearly constrained. So you have here a linear constraint. And contrary to the original constraint, which is quadratic, that makes the system much more easy to optimize. Well, a minimization subject to a linear constraint is basically a traditional minimization, unconstrained, in a flat subspace, while the original problem is non-linearly constrained, and it's much more difficult geometrically. You're doing a minimization on a kind of a sphere or an ellipsoid. So we avoid that, and we get guaranteed convergence for that in turn. The other thing is we avoid diagonalization. We can use mostly matrix multiplies for this minimization problem. And that is much faster, especially in parallel. There is a comparison here between a diagonalization-based optimization and this new method, the orbital transformation method. And you can see that especially as the number of basis functions increases, the new method becomes significantly faster than a diagonalization-based approach. Now, since it's a minimization, we also have things like sparse or non-sparse preconditioners to make the minimization problem solvable as easily as possible. It really is remarkable if you think we have kind of 10 million variables, and we are able to find the minimum of this functional in like 10 iterations or so. So that is really extremely efficient optimization of the unknowns. So intermediate summary here is that, okay, we have a lot of functionality. We can do DFT calculations and also other related calculations. We have very efficient algorithms to deal with large and inhomogeneous systems. What I should add now is that for small systems, the dominating part of the algorithm will be the calculation of the energy and the derivative. For large systems, the dominating part will be the actual optimization, so dominated by linear algebra and DGEMM. Now, the question is, can the underlying method be parallelized well? And I will try to answer that, and I think the answer is yes. So this is local DFT, GGA. This is scaling plots for systems of increasing size. And it's also historical data. So I first have data obtained on the XT3, Palou that was here. And that's the red curves. And now the black curves are the results we have obtained on the new machine, but also the new code. So it's not the same code. There's a lot of work that went into improving the scalability of the code. And I will talk about what we did here. So here, of course, the dashed lines are ideal scaling, which we get reasonably close to, depending on system size and the core count. The important message is that we're working on the code, and we get reasonable performance. This code, this results in this way, this would be kind of strong scaling if you follow a single line. If you increase the number of cores, if you increase the number of cores and you increase the number of atoms or molecules in our system, we can look at weak scaling. For example, this is a simulation of n water molecules on n cores of ROSA. You see, if we increase the system size, for example, if we would run 64 waters on 64 cores, we find an overall efficiency of the code of about 65%. What you also see is that the efficiency is actually better at the endpoints. So small systems are better, have a higher efficiency, and large systems have a higher efficiency. But in between, the efficiency drops to about 50%. Now, the reason for this is that in the very small regime, the the linear algebra, which is PDGEMM basically, is very inefficient, but also not very important. While for the larger systems, the linear algebra becomes more important, but also more efficient. But in the intermediate regime, the linear algebra is already important, but not yet very efficient. So this is, I will come back to this. This is important if you want to push the intermediate system sizes, which I would say right now most important for science. If you want to push the efficiency of these calculations, we have to improve the performance of the linear algebra of these systems. Now I will go a bit through the different data layouts we have. We have very different algorithms in the code, and all of these become important depending on the system size or depending on the number of cores. So the first thing is linear algebra. I mean, most of you will be aware about scalapack. This is the scalable linear algebra package. The underlying distribution is useful for dense matrices, so matrices that contain no zeros, and they are distributed in a 2D block cyclic way. That means that you have a processor, 2D processor grid, so you will separate your n CPUs in a P times Q distribution. This is also the reason why CP2K performs usually better if the grid is square power of 2, because then this distribution is kind of optimal. And in principle, the communication goes as 1 over P, while the computation goes as 1 over n CPU, so both parts scale. And if M is sufficiently large, M is the size of the matrix, computation fully dominates communication, and you would get very good efficiency. However, in CP2K, the typical matrix sizes are smaller than what people would usually do to, for example, do a linpack benchmark, and we don't get the real performance you hope for. So this is actually the sizes that are relevant. So this is the number of basis functions. That's the number of electrons. And you see these are relatively small matrices. It's 10,000 elements. It's a rather rectangular matrix, so it's 10,000 by 1,000 elements. So let's look a little bit at this. Yeah, I actually repeated the numbers here. So the ultimate operation for a DFT code is the this linear algebra operation. You have to compute an overlap of the wave functions, so the transpose of A times B. In CP2K, because we have Gaussian basis sets, the dimensions are about 10,000 by 1,000 for 256 watts, while for a plane wave code, that's the typical code that scales normally rather well on these kind of architectures, the number of basis functions is much larger for the same system. So you have about 100,000 basis functions, meaning also that is typically the difference you see in performance between the two codes. CP2K can be ultimately about a factor of 10 faster than a plane wave code. But if you want to scale well, good performance here is crucial. Now, that is kind of a performance measurement of PDGEMM as a function of block size. You can see there is quite some dependence on how you block the matrix. We have to pick the optimal values. That's what you also see, and this is unfortunate. You see that this operation doesn't get very close to peak performance. So that's actually a message for John, and I know people in this team are working on that, is trying to push the performance of PDGEMM for these small matrix sizes closer to the peak performance. That would bring us a lot. Then one thing we investigated is, because that's the direction we want to go in the future, is if you mix OpenMP and MPI, what can we get for threading? For example, here you see that on a threaded multiply, you get much closer to peak performance. So on this machine, peak performance is about 10 gigaflops. And you see that with 4 threads, we're actually getting quite close to, well, what is it? 80 or 90% of peak performance. And that's much better than what PDGEMM gets on, this is within one node. On one node, there's only 50% of peak performance. So maybe there is something we can do there, combining OpenMP and MPI linear algebra parallelized. Now, that's rather standard. What other kinds of matrix formats do we have? We have sparse matrices. If systems become very large, the derivatives become partially sparse. So certain number of blocks, interactions between two atoms that are very far apart, are going to become 0. So we have a kind of distributed sparse matrix format where we retain atomic blocks. Unfortunately, for this kind of matrices, they are sparse for us, but not in the traditional sense. So they are maybe 20% occupied for the really large systems. So they're not sparse in the sense of, finite difference codes where the occupation of the matrices is much, much, much smaller. So 20% occupied is for us already a rather large sparsity. We try to exploit that, not so much at this point, not so much in the communication, but in the local multiply. So ultimately, the scalability of the dense and the full matrices is roughly the same because the communication is similar. But we're working hard on a new sparse matrix library, which will also exploit the sparsity in the communication. So ultimately, that should improve further the efficiency. Other things we do, we have to do FFTs. So we have a regular grid. And one of the developments we introduced in the last year was how we decompose the FFT grids. We had a 1D distribution, just planes of the FFT grid. But that is not very efficient. As soon as you have more cores than you have planes, obviously, you get load imbalance. So we introduced 2D decomposition, allowing us to go much higher in processor count before the system gets load imbalanced. Typical grids are not huge. They are not small either. They are about 100 to 300 cube. That is a typical size of the grids we have. So obviously, with the 1D distribution, that limited our scalability to about 100. With the 2D distribution, we can go much further, basically, to Rosa size. The impact can be huge. This is an example. If you have a 1D distribution before on 4,000 cores, we needed a crazy 600 seconds. Switching to the 2D distribution, we get down to 18 seconds. So that is, of course, a very important way to improve scalability. Now, this is, in fact, much worse than if you would run it on just 1,000 cores. So you see here the all-to-all on this kind of distribution is really terrible. That is just a comparison of the scalability. So the red curve is the 1D distribution. The 2D, the green curve is an automatic distribution. The 1D distribution is favorable on small counts. The 2D distribution on large counts. The other thing we have is we have to map these Gaussian products locally. So we would like to, for every Gaussian we have, to be able to map it on the CPU in one single shot. So we need also a domain decomposition of our system. Each domain has a halo or ghost cells around it so that a diffuse Gaussian can be mapped fully locally. Then these, of course, these halos overlap with neighbors, and we can do a full 3D decomposition. The code automatically determines which kind of distribution is optimal, because you would like to minimize the halo volume. Sometimes you can minimize better with a 1D cut. Sometimes you can minimize better with a 3D cut. And then, of course, ultimately, you have a halo exchange to have on each local domain the full data local. That's then the cost of the halo exchange. You can see that, okay, either you have fully replicated or 1D grids. Of course, this is expensive. This doesn't scale. The volume is constant, or even since the number of CPUs increases, the time can go up. If you have the 2D or 3D decomposition, the time for the halo exchange, well, decreases, but doesn't scale well. So the halo volume is not 1 over the number of CPUs. It is scaling less rapidly than the number of cores. The other thing we have, another additional complication, is that Gaussians can be either very tight if you want to describe electrons close to the nuclei, or very diffuse if you want to describe valence electrons. And mapping them all on a grid with the same resolution would be a waste. You would use too many points to map very diffuse Gaussians. So we also introduced multigrids. Everything I've said here before should be seen in a multigrid sense. So we have Fourier grids in a multigrid. We have domain decomposition, real space in multigrids. And that is, of course, well, useful to map Gaussians with different range. And we do interpolation between these multigrids using FFTs. That is the most accurate one. Of course, it might not scale as well. The very fine grids are fully distributed. For the very coarse grids, it might be more efficient to replicate them. Coarse grids can have like just 10 to 20 points cubed, so that is only a very small grid that can be efficiently replicated. So that's the kind of layout we have. One thing we found very important is that this actually also introduces a way to load balance the system. If you have a very inhomogeneous system, for example, a cluster in gas phase, then if you have a real space decomposition, the central CPUs where the cluster resides will have a lot of work, but the far away CPUs would have no work. Now, with a multi-grid decomposition, you can swap the location of the CPU depending on the grid. So you can have, on the fine grid, your CPU will be working a lot on the central part of the cell, while on a coarser grid, you give it a grid that is not so loaded. And in this way, you can load balancing by basically changing the topology on each of the grid levels. One nice thing for this is that we have an accurate model to predict the load that you will have given a region in space, and that's shown here. So the model here, the black dots here are measurements, and the red curve is a prediction of the load before we actually did any computation. And that's what we try to load balance. So you can see, for example, if we increase the number of cores, at a given point, the granularity doesn't allow us to do perfect load balancing anymore, but the model perfectly predicts all spikes in the work. So as soon as we load balance the model, we have also a calculation that is equally well load balanced. So at that point, we don't need to do any dynamic load balancing. And here you see, for a kind of a worst case scenario, a big water cluster in an even bigger box, which is kind of very difficult to load balance, the effect of load balancing over the multi-grids. So you see, this is very badly load balanced. There's a factor of 10 more work on one of the CPUs than the average. Well, if we do the balancing on the multi-grids, we can level the work. And if we tune the multi-grids, if you have the right number of multi-grids, we can get an even better result, almost quasi-perfect load balancing. Now, that was a short overview. That's the kind of simple formula I wrote down in the beginning. We have Gaussians, and we will want to map it on a real space grid. We want to Fourier transform the grid. That's the kind of operations we have to do. We have first a distributed sparse matrix. We have to rescatter the elements of this matrix so that Gaussians can be computed locally. In order to do it locally, we have a 3D decomposition of the grid. Each of these 3D regions has a halo, which is necessary to map these Gaussians locally. We have halo exchange. We have then a transfer from this 3D grid to a 2D Fourier grid, and we can do a parallel FFT of that grid to get the density finally in G space. So that's the relatively complicated algorithm that brings us this simple formula in the implementation. And that is the efficiency we get, at least for the small number of CPUs. They are fully dominated by this part of the code. Now, I told in the beginning there are two parts in the code that are very important. It's the calculation of the energy and the actual optimization. And here is just an analysis of the fraction of time spent in these two parts. The full time is shown here. The fraction of time spent in the Concha matrix construction, that's the energy calculation, or the time spent there is shown here. You see that for the smaller system sizes, which are the system sizes that were possible up to, say, 3 years ago, basically most of the time is spent in the Concha matrix region. But now, as we move on, you see that most of the time is actually spent in the remaining part, in the linear algebra part. So this is, again, the message that we have been very proud on our very efficient algorithm for the Concha matrix construction, but we should now really shift direction and try to work on the linear algebra to get that part scale very efficiently. Now, is the Concha matrix part really done? And of course, the answer is here, no. We have recently implemented an extension of our code. We've introduced more accurate functionals. So density functional theory comes in various flavors. You have more efficient but less accurate approximations, and you have more expensive but more accurate calculations. And of course, the direction is towards more accuracy. People want to have better chemistry. They want to have, tell me.
before you move on, when you say the linear algebra, that's subspace diagonalization?
Yes, or this orbital transformation method, yes. Or any new ID that might come up there. So,
I know, but the reason I'm asking is because that seems to be, as you go with even plane wave methods and other methods, it seems to be that the bottleneck.
It's the bottleneck. And plane wave methods even more, because they have much more basis functions. So this is the part in our case that is like 10 times faster than the plane wave code. But it scales the same way. So it's just a prefactor that is a factor of 10 smaller. But ultimately, it's the same problem we have to solve. And of course, any good ideas in the plane wave codes can be transferred to our code as well. But we can go one step further, and that's what we want to do. For these large systems, we can start exploiting the sparsity in our localized basis set. So contrary to plane wave codes that are like stuck to this cubically scaling approaches, we will be able now to go to linear scaling approaches. And for the larger systems, this will be possible. I mean, it hasn't been really interesting for systems, say, smaller than 500 atoms, because there is no sparsity. But once you move beyond 500 atoms, you come in a regime where new algorithms, linear scaling algorithms, might be really interesting. And that's why we started investing now so much in this new linear algebra, sparse linear algebra package, because this is going to be the future. For large systems, we want this linear scaling, and then we can move on. Yes?
The linear algebra part of your code, you're using just the standard scalapack full parallel. Do you divide, you just, example, if you divide your problem, you have different matrix size, and you divide it by the CPU which you have, you just, if the CPU gets the small matrix, they will get, they do the diagonalization and they will finish. They stay without doing nothing.
No, basically right now all CPUs are working on the same matrix at the same time. So there is like no parallelization over the different matrices. There are actually not so many different matrices. I mean, ultimately, the central operation is the calculation of the overlap matrix. I mean, this has to be done. And that is going to be the bottleneck. Well, it is kind of the bottleneck. So, yeah. Is it answered your question? So then I want to talk about this new development. So given that machines get more and more efficient, we can go to a new level of accuracy. That is, we can add to our functional that I showed before an additional term. And this is this term. It looks also relatively simple, this Hartree-Fock exchange. This is, if you look carefully, this is kind of a vector transpose a matrix and a vector, and then with minus 1/2. So that's the operation you want to do. The matrix M here is given by these objects, and each of the matrix elements is just an integral, actually a 6-dimensional integral, but quantum chemists have found techniques to do that quite efficiently. You can do these 6-dimensional integrals analytically. But this is the kind of operation we would like to add to the code. Now, the particular thing about this is that the matrix sizes are really very large. So a typical, or for a relatively large system, but the system that we already run here at CSCS, the matrix is going to be 10 to the 9 times 10 to the 9. So it really is a very large matrix. Already the vector here can be several gigabytes in size. Now, computing the matrix elements of this matrix is analytically possible, but expensive. So if possible, we want to store the result of our calculation. Now, obviously, 10 to the 9 square, 10 to the 18 elements you cannot store, also not nowadays on the biggest machines. Now, the good thing is that many of these matrix elements are actually 0. So a very large fraction of the elements is 0. And so you have to decide which elements to store and which can be ignored. And so this is just to give you an idea. One of our largest calculations so far had about 10 to the 18 matrix elements. And we could screen, or we could decide on which elements are 0 and non-zero just using 10 to the 17 flops. So you have to be very efficient in throwing away matrix elements. Also, you have to be able to throw away bunches of elements at the same time. And then if you're able to store these elements, these matrix elements, you can do what is called in-core steps. You can just run over pre-computed matrix elements, and you're likely a factor of 10 faster. So we have to be able to explore that. We have to be able to store as much of these elements in memory and reuse them. That is just a kind of example. It's a very, small system for current standards. You see, if you have no trick implemented, the number of integrals is really incredibly large. And then by using symmetry and by having thresholds on these matrix elements, we can really reduce from like 3 terabytes of storage to ultimately less than a couple of megabytes for such a system. So it's very efficient to screen away and to compress elements. Do you have a question? No. OK.
What symmetry are you using?
We use all symmetries. No. Well, typically, large complex systems are going to have no symmetries. So we want to do MD. Our molecules just move kind of randomly. And there's no symmetry in the system, but there's a symmetry here. So there's an 8-fold symmetry. You can see that. Okay, you can exchange alpha and gamma, beta and delta, and you can exchange these 2 pairs as well. So there's an 8-fold symmetry there, which we want to exploit, because if we exploit it, we're 8 times faster. And actually, this was one important consideration. It's very easy to exploit the symmetry in a serial code, but it becomes much more difficult to exploit the symmetry in a parallel code. So there was one design choice that we want to exploit the symmetry also in the parallel version of the code. So contrary to the other matrix I mentioned before, this matrix M is really sparse, so we can get to something like 0.001% occupation. But nevertheless, even that non-zero part can be huge. There can be 11 terabytes of storage for one of the calculations we did. Now, the parallel algorithm, how did we implement this matrix vector product? We fully distribute the M, the matrix, obviously, because it's huge, but we replicate the vector. So each MPI task, I would say, has the full vector local. Now, given that this is a vector with 10 to the 9 elements, it actually is a really big amount of memory. So it's quickly a gigabyte of memory. But we replicate this. We send this around in a ring topology. We do the screening, so we decide which elements are going to pass the screening. Then, and this is very important, then we do a load balancing of M. We only decide at that point what work is going to be done by the CPUs. We do the work. We basically compute the result of this vector. So M times 3 we compute. We reassemble that then in a distributed way. And that's basically the algorithm. So the advantage of this is a relatively easy communication pattern. It's replicating the density matrix. It allows for easy load balancing, which is crucial. And it also allows for exploiting all symmetries. Now, the disadvantage is, of course, that it requires a lot of memory. You have to replicate this matrix V, and you also have to communicate this matrix V. And then the solution we had for this is, at this point, combining OpenMP and MPI. So the largest benefit for this combination is that we can share the matrix V, the vector V for all cores on the same node. And at that point, we gain a lot. Before, we could never do a system of this size, because if you have just 2 gigabytes per MPI task, you cannot store this vector of 10 to the 9. But now on the new architecture, where we have like 8 cores with each 2 gigabytes, we can easily store the full vector and the result locally. Then also, of course, if you replicate it only on a node, the amount of MPI communication goes down by roughly the number of cores. It also gets a factor of 8 faster. And then, this is a bit nasty, but it also helps us. The parts of the code that do not scale well, that would never scale up to 16,000 MPI tasks, such as diagonalization or the halo exchange, they also get reduced. And since they basically stay at the cost they have at 2,000 MPI tasks. And typically, these algorithms would grow very badly in cost. But we can, in this way, we can limit them. And of course, we rely on the fact that this Hartree-Fock exchange is about 100 times more expensive than the local part of DFT. So if we have the Hartree-Fock exchange very efficient, we get good results overall. This is the benchmark systems we've been running. Actually, John has been running them on Jaguar. So the goal here was to compute for a lithium hydride crystal, the cohesive energy, using no symmetries, no K-points, so that we can use it much more general, that we can also look at defects. And of course, that makes it a very difficult system. We have about 37,000 basis functions, so 37,000 square is the size of our matrix. We run it up to 65,000 cores. The real issue here was memory, so we had to work very hard on the code to have it actually fit on the 16 gigabytes per node. In going to so many cores and so many basis functions, you have to take really care. For example, the number of cores square already overflows a default integer. So if anywhere in your code you have this kind of computation, you have a bug. And they only will turn up when you run the code on 65,000 cores. So that is things we had to fix. You have to be very careful to protect against zero work. I mean, many parts of the code actually, there's not so much work remaining. For example, the FFT, there's less than 1 point per node. So you have to be very careful that your FFT is able to deal with grids that have no local points. There are strange things. So it turned out that the MPI performed better if we synced before and after the MPI at the given point. That was something you also had to find out just basically by luck. There's lots of stuff going on to do, for example, blocking, as we've seen this morning in the course, trying to block force-centered loops in optimal ways to reuse as much as possible the cache. Also helps with the OpenMP. The kind of blocked atomic updates of the result factor here are more efficient than if you just kind of randomly scatter on these blocks. And then working very, very hard on load balancing, get the load balancing perfect. This is not so easy. And basically remove any serial bottleneck in the code. It's remarkable how small, how limited the number of lines have to be to already show up in a profile if you run on so many cores. So you kind of have to be perfect. Anything that you thought would run fine if you tested on 256 cores is likely to show up on the full result. So that's then the kind of scaling plot we got out. This is the number of cores and the speed up. As you can see, the red line is the Hartree-Fock code. You see scales quite nicely, especially in the beginning. As we add more and more nodes to the system, we have more and more memory. And actually, we get a superlinear speed up because we store the intermediate results. And that's the first part of the calculation. So before, running on fewer than 2,000 cores in this case would be really bad for the efficiency because you're basically running in a mode that is really slow. Once you reach 2,000 cores, you have enough memory to really do the calculation efficiently, and then you see that we scale up to from about 2,000 up to 32 or 65,000, depending on what you look at exactly, quite nicely. And so you see that the Hartree-Fock part of the code still has more than 100% efficiency compared to running on 512 cores for this system. So I think that is a very nice result. Also for us, of course, being scientists, we care also about these numbers. That is the best reference number in the literature so far for the cohesive energy. That is done with K-points, exploiting our symmetries. We could ignore that, and we still get a result that is in perfect agreement with the reference number, like showing that we can do this calculation in some sense in a brute force way. Now, that is a crystal. People could do it differently. This is another example that people couldn't do so far. It's a fully solvated protein. We can now treat that with a good basis set. So there's always an issue in quantum chemistry. So this is a good basis set for density functional theory. We can treat the system fully solvated, fully periodic, and compute in about 3 hours on 8,000 cores here on ROSA the electronic structure of the system. And we can compare, for example, with cheaper methods. So we can do a local calculation on this system, and we can analyze the electronic structure. And you see, for example, here, that's a difference in spin density between the hybrid code and the local code. And you can see that the local code puts too much spin on these atoms here. So that's iron, that's sulfur, that's the iron-sulfur protein. You see local functionals have a tendency to delocalize spin density, and hybrid functionals correct for that. So that is, for us, the result. So this kind of calculation is now well feasible locally, 3 hours on 8,000 cores, and about 11 terabytes of memory. Now, that's still a single point calculation. What we really want to do is complex systems and ab initio molecular dynamics. And that's also an example that we did here. That's an interface between liquid water and titanium oxide. You can add electrons to the system. That is important in all kinds of catalysis. I mean, that is anatase, or no, sorry, rutile. That is used, for example, in paints, but as a catalyst as well. And that's the kind of time we get. We do MD, so we move the atoms by half a femtosecond, and that requires about 250 seconds of compute time on 4,000 cores. And that's 80% parallel efficiency. Now, one thing I want to point out, and that makes it very difficult sometimes to estimate in advance how expensive a calculation is going to be, there is this screening parameter. And depending on the precise value of this parameter, the cost of the calculation actually changes dramatically. So at 10 to the minus 7, we, for example, only need 0.1 terabyte of memory. If it turns out that because of technical reasons we need a screening of 10 to the minus 9, suddenly the calculation becomes 10 times more expensive. And that's something you can only find out doing the calculation. So that makes it difficult to estimate within a factor of 10 how big the calculation is going to be. But with this setup, we can perform molecular dynamics. Here you see the potential energy of the system is actually quite nice and stable. And the conserved quantity of motion, as should be, is basically a flat line. Now, finally, I would like to acknowledge people. I would like to thank, in particular, Manuel Guidon, who is the PhD student in the group that has been working in the last 3 years on the hybrid code. This is in the group of Jörg Hutter, all at the University of Zurich. I would like to thank here John and Jason, who made it possible to develop the code in the first place. Then, for the local DFT part, Ian at EPCC, he has been sponsored by NAG to work on the scalability of CP2K, Halo exchange, and the 2D domain decomposition. There was a collaboration with Ben Slater at UCL. Then there is CSCS, where we do the bulk of our high-performance calculation. I also got in touch with Pekka, who is at the Finnish Supercomputer Center in the context of the PRAISE project. And I would like to thank you for listening to my explanation about the code. Other than questions?
Question. I'm trying to understand the Fock term there, or the exchange integral. So the matrix.
This one.
Yeah.
Yeah. So the point is, and this is
the Fock matrix that you're talking about.
No, it's not. This is the total energy. It took me about 3 years to see it, that we're actually doing the simple matrix factor multiply. And the reason is that people write it like this. But the vector here is actually the density matrix. So V is my density matrix, and the Fock matrix is M times V.
So the matrix is just this integral of
M. M is this integral
of orbitals.
Of basis functions.
Basis functions. And the basis functions, what I'm trying to find out is that you move your MD simulation. How much do the basis functions, they don't change? Or
they do change because we use Gaussians. We have atom-centered.
So you have to update the matrix
every MD step.
Every MD step.
Yes.
But
not during the self-consistent cycle.
Not so you.
We do Born-Oppenheimer MD, not CPMD. That is one important thing here. So we do Born-Oppenheimer step.
How many cycles do you have that consistent?
It's very system dependent. So like for water, we will have maybe 5. For the electron in the titanium oxide interface, it might be 15. For the protein, if you start from a GGA gas, it might be 35.
Okay, per MD step.
Yeah. Yeah. So it's very important we can save it. I mean, we gain between not having the matrix M in core and out of core. It's overall at least a factor of 5, and depending on the system, it can be even up to a factor of 100.
You would save the matrix in memory.
M is in memory.
M is in memory during the self-consistent.
Yes. Yeah, and then it's thrown away once we did an MD step. Actually, we do use some information in the MD, and it's important, in fact. But our load balancing for the first step is not perfect. I mean, it's very difficult to estimate how much it's going to cost a given block of integrals. But in MD, we can use the fact that the integrals don't change too much. So the cost of a given block, we call it a bin, it's a bunch of integrals, changes in a rather continuous way. So load balancing during MD is dynamical. So we measure the cost of the bins, and then in the MD, we use the measured data, which is very accurate, to do the load balancing. Then in MD, we get almost perfect load balancing.
Okay. I may have more.
Earlier, when we were talking, you mentioned that the next step for optimization is much more difficult.
Yeah.
And what is
Distributing this guy. And, well, that is easy, but retaining the load balance on the product. So that is very difficult. So, and also making it even more difficult is the fact that all these symmetries are there. So basically, if you have one element of this vector, there are 8 places where you have to use it, and you have to store it in four other places.
So distributing V means distributing over the course on the node? Or you're
No, over the nodes. I mean, right now, well, it's shared between all the cores. V is shared between all the cores on the node.
on the node. But
Yeah.
you have V on every.
But the full V is on every node.
Yeah.
Now, what we really would like to do is to distribute V, in addition to distributing M, retaining load balance and retaining all symmetries.
And that's because V is going to grow.
Well, V is already like 10 to the 9 matrix elements. So that is like 4 gigabytes. Okay, we have symmetry in V as well, in fact. So it's 4 gigabytes. And we have V and we have the result. So that together is already 8 gigabytes replicated per node. And then since we really want the memory to store M, that is a lot of memory that is. So, I mean, we have the IDs here.
And V scales linearly with the system size.
Quadratic. Well, that is another step that we are trying to. I mean, ultimately, V becomes sparse as well. I mean, it's the density matrix.
Yeah, that's one.
Yeah. Now, as I said, it's between 20 and 80% sparsity. For example, for the protein, which is really not a small system, V or P is 80%. Sorry, V is 80% occupied. So we already exploited actually now in the storage. So V is already this sparse symmetric matrix, so to say. So for this system, this is really large already. So this is I think 3 by 3 by 3 nanometers. And at that point, the sparsity is just setting in. So no more questions?
Okay.
Thank you.
more questions?
Yes?
Yeah, the diagonalization stuff. Is it like you diagonalize by block?
No, it's a direct minimization. So we kind of avoid diagonalization. I mean, this is really what we have. We have E that is a function of the density matrix, which is a function of the C, the MO coefficients, which is a function of X. And then we're going to just compute the E, the X, and pass that to conjugate gradient algorithm. So we have to write that down. And you can do that. It turns out that is rather doable. And also here is actually, OK, the most difficult thing is that these are matrix functionals. So X is a matrix, S is a matrix. So here you have the overlap. X transpose SX is kind of an overlap matrix. That's going to be a 1,000 by 1,000 matrix, roughly, say. And then you have to compute the cosine of the square root of that matrix. Now, you can either do that by diagonalization of a 1,000 by 1,000 matrix, or you can do it with a kind of Taylor expansion. And so, again, in the first step of the SCF, we will use diagonalization because X can be a large matrix, have a large norm. And that's relatively expensive and in particular doesn't scale well. So what we really would like is to have a 1000 by 1000 matrix scale on 1000 cores. Now, it's going to be tough. But if we are further, if we're propagating in MD, X becomes a small number and we can do a Taylor series, and then we can do a matrix multiplied based calculation of this. And that scales much better than a diagonalization based calculation of that. And that's also what we use in MD. So the first MD step is normally slow, and then afterwards we become faster.
Another question, just what was the correctness of the result when you search the one term of the energy? But with this approximation, if you compare like the pure DFT calculation, what was the correctness? Are you they are comparing the results, or
this is very system dependent. So standard DFT, local DFT, I mean, is known to work very well for a lot of stuff. So like structures of molecules and so on, they look rather well. But as soon as you look at particular things, and for example, reaction barriers or the localization of electrons or spins, then local DFT becomes not so good. I mean, it's not
Local, you mean LDA?
LDA, GGA, yeah, local. Semi-local. So GGA is not so good for reaction energies and like electronic properties sometimes. And then you can add this term, and that improves the results. And what is very important, I think, here is that most of the development in functional development is now focusing on these hybrid functions. So all new stuff, or most of the new stuff, has some hybrid character. And if we don't want to be stuck, I mean, in the material science community to local DFT, we have to like catch up now with the quantum chemists. I mean, first material science and physics was first. They adopted DFT very early, and then they stayed very long now with GGAs. And quantum chemistry is moving in these hybrid functionals, and they really are much better for reactivity, for example.
But there's hybrid functionals and hybrid functionals.
Yes, there's a zoo.
So the only thing you do is add the exchange term.
Well, no. I mean, we try to implement these new functionals. I mean, you have, for example, screened exchange, the HSE functional. That is a different shape of the operator. Also, that is implemented, let's say. So, and then we try to do many of these hybrid functionals, but you cannot follow the literature. Sometimes it's difficult to do that.
Because hybrid functionals, there's a lot of cooking.
Yes, we like that. Lots of knobs to. Lots of knobs to.
So the reason why I'm asking is because there seems to be a value, particularly in terms of future architectures, to think about this exchange integral. Mm-hmm. But on the other side, the thing that makes physicists nervous is that the reason why LDA and GPA works is because you have these cancellations of errors between the correlation and the exchange term.
Yes.
Approximation.
Yes.
Which you throw out basket with doing the exchange term. Exactly.
Well, the point is, yeah, I of course see your point.
Why we, for example, don't really go often in condensed matter physics in direction of exact exchanges because things get better, like you describe localization better, but other things can get worse.
Yes, but this is the point I think that lots of progress has been made in the last 3 years, say. Mm-hmm. So up to recently, it was like certainly not possible to combine 100% of exchange with a reasonable functional. Yeah, and that's why people use, for example, PB0 with whatever 20% of exchange of 25. But now people work on that, and there are functionals now that take into account the static correlation. So a normal exchange functional was relatively good because it also mimics static correlation. And now people start developing functionals on top of 100% Hartree-Fock exchange that also take into account static correlation. And for example, Becky has a functional that uses 100% matrifoc exchange plus a static correlation functional. And it's increasing. I mean, there's lots of work now by Scuderia. I mean, Scuderia is moving towards condensed phase as well. And for example, they have the the HSE, the screened exchange functionals. And they are much better for band gaps, for example. I mean, there are relatively reasonable predictions of the band gap. And it might come. I mean, also other people, Gross, for example, is working on, density matrix functional theory. Now, that is something that looks like completely different, but computationally, the kernel there is also exchange. So this is not implemented, but that would be not so much work to add, for example, a DMFT functional. And they certainly, there's lots of stuff that I think is evolving there, and I think it's essential that we have like the code now that does this and that we can move on.
The version you did use is the version available in CBS.
Yeah. Always make everything available.
For the larger jobs you did in Jaguar, is with the approximation QM, quantum QM and M?
No. These are all full QM calculations. Sorry? Hybrid functionals. DMFT is not implemented. I said it might be possible. This is something that could be added. But no, density matrix functional theory. There are two theories that go under the same abbreviation. Good, thank you.